Let me introduce you first. So Charles Neslund is a scientific officer for Eurofin's Lancaster Laboratories Environmental and the PFAS practice leader for Eurofin's Environment Testing United States. Charles has worked in environmental analytical chemistry for over 36 years. He is a subject matter expert in high-resolution mass spectrometry and PFAS analysis. Charles initiates new methodology and directs research and development at Eurofins. He is also responsible for identifying trends in analytical testing and equipment at Eurofins. Charles will speak on challenges associated with analysis of PFAS in food and food contact materials. Take it away, Charles.
Thank you, Neil, and thank you and Ilse very much for inviting me to present here today. And also I wanted to thank Keith and Susie. I think their presentations were terrific. So thank you very much. And I think folks will see that as I go through, there are elements of what I'm talking about that tie into both Keith and Susie's talks, what to me is always the fascinating thing for all the years that I've worked in environmental and analytical chemistry is how different folks from different walks of life and different disciplines come across and to the same end objective as one another. So anyway, with that, a little bit of intro or to give some perspective on PFAS. I know both Susie and Keith did at the beginning of their talks, their discussion, but to point out, I mean, we talk about PFAS, but PFAS really formally is a very large group of materials, and Keith mentioned 47, greater than 4,700. Well, those are actually, the greater than 4,700 are actually the non-polymeric forms that we know are potentially out in the environment and potentially in contact with food, water, and other things that we consume. Polymeric forms are also formally PFAS, although the polymeric forms, the ones that we're familiar with regard to Teflon, FTFE, PTFE, other fluoropolymers like that, which are so essential to many aspects of our life, are also PFAS, but not what we're currently concerned about in our food products, in the environment, in our drinking water and like. And even within the non-polymeric forms, there are multiple classes of compounds to be concerned with. In the total list of 4,700 compounds, under that, we actually have several broad chemistries like anions, cations, Zwitter ions. There are also neutral compounds like fluorotelmer alcohols that are acrylates that are potentially of concern. But most of what we're talking about here today and the analytical methodology that we're talking about is addressing the anions and those things that were used in AFFF, other surfactant processes used in the manufacture of polymers. So despite the concern for PFAS in drinking water, and as you know, Keith pointed out, drinking water is a lot different, a lot easier than the packaging material. I think there's some of us that might disagree with a little bit. I think there are elements there where it's different. It's a different game. In drinking water, we're looking at extremely low levels, and in fact, when we're talking MDLs, there we're at sub PPT concentrations for many of those if we get down to an MDL level. But they bioaccumulate. They can be found in the food chain. Typically see them partitioning the protein, and not like other persistent organic pollutants that we've had to be concerned about in our food chain, like dioxins, PCBs. Those are all lipid soluble and lipid seeking, whereas PFAS are not necessarily so. And the big concern is that they're not metabolized, or if they are a form like a polyfluorinated form and they do metabolize, they typically go to a more terminal form of PFAS, like the perfluorocarboxylic acids. So from a bioaccumulation standpoint, and this was an environmental paper. I know we're talking food here, but in an environmental paper, because I think this applies, if you look at this longer PFAS or longer chain, which was mentioned in earlier talks, are more bioaccumulative in animals. And you see the chart over there on the right where the shorter chain, like the butanoic acid, the pentanoic acid, are less bioaccumulative in animals, whereas the longer chain, say an octanoic acid, an octane sulfonic acid, the nonanoic acid, so C9, those are more bioaccumulative in animals. But in plants, it seems to be the opposite situation, where you tend to see if there's some bioaccumulation. And from an absolute amount of bioaccumulation, I think we're looking at an order of magnitude or so different. But you typically see the shorter chain, the C4, the C5, that tend to be bioaccumulate in plant material more so than they do in animals. So much of what I'm going to talk about here next is really talking about this from the point of a contract laboratory. So in our case, you know, we go to contract laboratory, so it's a commercial need, a commercial endeavor, and also we're, for the most part, where there are published multi-lab validated methods, that's what you're expected to use. That's what you're expected to be certified, and what your quality systems are built around is those multi-lab validated methods. Well, when we first started doing PFAS, and actually for the drinking water method back in 2008, 2009. And then as PFAS became environmentally much more of a concern at certain sites in the 2015, 2016 kind of time frame, I mean, what reference point do we have? Our reference point is an EPA method for drinking water. So that's what we know. That's what we are familiar with. That uses a solid phase extraction, which was some of what was talked about earlier in Susie's discussion when she talked about those wax cartridges. But in this case, they used a different chemistry. EPA used a different kind of chemistry, something called a styrene divinyl benzene. And there it actually functions based on hydrophobic interactions. So if it's a hydrophobic interaction, that long tail of a PFAS compound, whether it's a C8 or a C9 or a C10, those compounds are adhered to really well. They extract really well. But when you get down to shorter chain compounds like the C4 and the C5, that kind of chemistry just doesn't work as well for extracting them out of water. But the main intention of the current EPA method 537.1 was originally to address PFOA and PFOS, for which there were some health advisories set in drinking water, and then more recently to add in these replacement compounds, Gen X, or you'll see the acronym HFPODA, ADANA, the F53B major and minor, that were replacements for PFOA, PFOS, to a certain extent PFHXS in some of their common industrial applications. So for the most part, that's where, if we're going to have to do matrices outside of drinking water, where's a contract laboratory going to go? They're going to base it on what they know, what they're certified for, what's multi-lab validated, and then modify to be able to address the other matrices. Just recently, the end of last year, EPA put out a new drinking water method, but still drinking water, and that was 533. Uses SPE also, but has gone to this wax or weak anion exchange chemistry for the extraction. And here the advantage in that, and you'll see in the other applications, in the application we set up within our laboratory, we use that weak anion exchange chemistry for the extraction, because it takes advantage of I'll call it the head of the molecule, that carboxylate anion, the sulfonate anion, excuse me. And so we get better selectivity on that extraction, and also think that we can extract a wider range of PFAS compounds. So then there's the EPA 533 method out there. I know this slide's a little bit small, so bear with me, but I was trying to show you. So if we look across a list of compounds, here are the kinds of compounds we've got that are covered by the drinking water methods: carboxylic acids, sulfonic acids. There are a couple of sulfonamidinoacetic acids. The newest method has some of the fluorotelmer sulfonates, and then also some of these perfluoroether carboxylic acids that are some of the replacement compounds. So the commercial laboratory like ourselves, what would we do when we're asked to do food, asked to do vegetables, fish, some of the various kinds of products that Susie mentioned. And for us, it wasn't that we were going out and doing a market basket study or a survey. We have clients that have a concern. They learned about their dairy cows drinking water that they learned now was contaminated with PFAS, or eating from fields in which they had applied biosolids, or vegetables that were grown in fields where biosolids had been applied and or irrigated with PFAS contaminated water. So that concern is, we need you to look for these compounds. Do you have a method? Well, again, 2015, 2016, there aren't published established methods. And what Susie showed that FDA has done more recently is terrific. And what we're looking for then is multi-lab validation, and what Palmer's going to be talking about here in a few moments. But anyway, so we would set up a method using what we know. It's LCM-SMS. It's a targeted compound analysis. We're going to use isotope dilution, and that was mentioned previously, and I just want to talk a little bit about that because I think the isotope dilution is what is really strong for getting us through these various matrices. So isotope dilution, very simply, is where we've got a compound that is essentially exactly the same as the target compound that we're analyzing for. So in this case, I'm showing C13 PFOA, and you see I have a couple of the carbons there that are C13. Most carbons are C12. 98.9% of all carbon is C12. Well, if we've got these isotopically labeled compounds, this C13 PFOA, and in this case, there's 4 C13s, or there could be 2 C13s, or 3 in that structure, depending on how it was synthesized. It extracts out of a matrix like my native PFOA. It's going to chromatograph like my native PFOA. It gives me a retention time marker for my native PFOA within the sample matrix that I'm analyzing. So it is as if I spiked the sample with PFOA, but because it's the C13, its molecular weight is just a little bit more than PFOA. So with our mass spec, we can discern the difference between those. So then doing that, and here's another small, so if I get yelled at for anything today, it would be that I've got these slides with a lot of small writing on it, but wanted to show you, so this expansive list that we're able to do, and if you look down the column with the check marks, with most of the X marks in it, is what our routine list of 40 compounds is. Now, these are targeted compounds. This isn't getting into some of the non-targeted work that Keith was talking about, but targeted compound lists that we're able to do and use an isotope for most all of those, not all, but most all of those, able to use an isotope dilution application. So not, like I said, not a lot of validated methods. So the approach that we would decide to do, or that we're asking, what would we use for vegetables, fruits and vegetation, dairy, meats, all those kinds of matrices? We're going to want to use something that, number one, is isotope dilution, because it will show us the actual recovery of the target compound that we're interested in that specific matrix. So in the absence of a multi-lab validated method, or a method that has been built and developed specifically for cheese, or specifically for fish, or specifically for carrots, we've got a way to get a great handle on the performance and extraction performance of these compounds within each one of these matrices. So we also then take advantage of the weak anion exchange chemistry. So much of what you heard Susie talking about, which is we extract it, we blend it with some organic solvents, and then remove that from some of the residuals. What we also did was we used a sorbent and a binding agent. So we would blend it with a binding agent, which a lot of the pigment, a lot of proteins, a lot of other high molecular weight materials that were potentially going to give us problems would bind to this binding material. Then we used organic solvents to pull the PFAS off of that blended mixture, and then took that solvent mix, concentrated it down, and then we would put it through a weak anion exchange cartridge for an additional extraction, isolation of the PFAS, and in some cases, depending on the material, include PSA and or a carbon-based cleanup. So you see the commonality with what Susie had set up, and this is something that we had set up and worked on several years ago to be able to offer to clients and customers. But look at the commonality between, and honestly, before this interaction, Susie and I didn't know each other, but yet we've come to, I think, relatively similar or common places in this method. So in trying to move along here, here's another lot of a busy slide, but it's a 2-page raw data piece just to show you where we've got this list of these isotopically labeled compounds, the extraction standard peak table that I have over there, and their recoveries in this particular matrix, and then your targeted compounds analysis, for which all of those results, you see some low-level detections in there, but nothing that quantified above what the MDL was. The other thing to point out is that is a concern here. The targeted analysis with LCMS/MS is a terrific analytical technique, but as we've gained experience with these, or we've learned some things like, for example, this was from the analysis of eggs. So with eggs, we were seeing this peak, and you see on the, and this shows as PFOS, but in the middle plot there, that transition from 499, mass 499 to 80, you see a peak, it's not shaded in, and it's shifted over to the right. Well, looking at this, and you think, oh, well, maybe that was just a little matrix that shifted that peak over a little bit. Well, actually, this is a chromatogram of a bile acid, taurodeoxycholic acid, which in things like eggs can become a problem and produce a false positive if you're not aware of the possibility for that potential false positive. I mentioned fluorotelomere alcohols, so I mean but again, to point to the fact that PFAS, not all PFAS are anions, not all PFAS can be done by LCMS/MS, not all PFAS can necessarily be done by the exact same, even if it's an exact mass analysis, because sometimes these cleanups that we talked about before, they perform essentially a discrimination on your sample based on whether they're anions, cations, neutrals, what have you. So you have to be cautious about what kind of extraction and processing you're doing of your sample prior to that analysis. And then these things have already been brought up, but again, as a commercial laboratory, these are things that we have or have worked on putting in place for our environmental clients, but they found great use for clients that have food products that need to do the analysis. And the total oxidizable precursor, just very quickly, is really where it says it allows us to use our targeted compound analysis, but it says there are potentially compounds present in your sample matrix that can be forcibly oxidized to the perfluorocarboxylic acids. So I can analyze for the perfluorocarboxylic acids really well. Some of these other compounds I might not know or be able to see, but under laboratory conditions, I can sort of force the oxidation of them to these perfluorocarboxylic acids, which then gives me an indication that there are other PFAS present that I may not be able to specifically target or see, but would have some sense of being able to detect their presence. And then the total organic fluorine, combustion ion chromatography, which Keith mentioned, which can be applied to water, solids, soils. So, I'm not going to spend a lot of time there. And then, of course, the non-targeted analysis, which is a new area for us. We in fact are using a QTOF, not an Orbitrap, but a quadrupole time of flight mass spec that can give us exact mass and can do all of the kinds of things that were talked about before. Basically finding knowns and what we're calling known unknowns, those that might be found in our limited libraries. We've got libraries of hundreds of compounds, fluorochemical compounds, not the tens of thousands like we have in other GC mass spec libraries, but something that could help us to do an initial sweep, and then of course isolating it to unknowns. And with that, I think I ran a little bit over, so I do apologize, but I want to thank everyone for their attention, and thank you for the opportunity.